In Chapter 7 of the ECE 301 workbook, we finally get to move beyond resistances and now consider the other important circuit elements, inductance and capacitance. We're going to start off with capacitance, and then we'll work our way into the next one, inductance, in later sections. So recall capacitance is a circuit property that accounts for energy stored in electric fields. So that's important because inductance is similar. It's a property that accounts for energy stored in magnetic fields. So if the energy is associated with magnetic fields, think inductance, electric fields, think capacitance, right? Some examples: transducers are designed using both inductance and capacitance. In a microphone, for example, capacitance changes with sound pressure, right? And mutual inductance is the foundation or the basis for transformers that are used to transmit electrical power over very long distances, all right? So section 7.1 on capacitance, we'll talk about how they're constructed. Basically, they're consist of the separation of two conducting plates. Usually they're metallic, and they're separated by a thin layer of insulating material, right? So we'll just sketch one, just a very simple design of what a capacitor or capacitance, we'll say, looks like. So we have two conducting plates. So I'll draw one plate here, okay? And I'll try to do it sort of in a three-dimensional setting here where we can see another plate coming out here like this. Put an edge around this plate like that. And then what we have between the two plates is this material, okay? So it's kind of a skewed version here, terminal coming to the top and coming out of the bottom there, all right? So the idea is that these two plates illustrated here are conducting plates. And the inside here, that layer has a name. It's usually called the dielectric layer. So what could be between these two conducting plates, right? A couple of examples. So the examples, let's say, of the dielectric layer, nothing. In other words, air, sort of a vacuum, okay? Nothing inside, right? Or some other materials, maybe mylar, polypropylene, or perhaps even mica. Okay? All of those are good insulating layers, right? So natural question is, what happens to the current flowing through a capacitor? So a current comes into the capacitor. So we're going to illustrate what happens, all right? So now it's sort of flipping the capacitor on the side here, taking a side view. Here's one plate. Here's the other plate. Here's the terminal and the current's coming in. So we'll just write current's coming top to bottom and leaving out through this. And of course, the inside here is that dielectric layer. Again, here's our dielectric layer. Okay, all right. So what happens here is the charges of opposite signs will collect on the respective plates. So I'm going to illustrate that this way, but the top plate, we would get all the positive charges accumulated, and then the other plate will have the negative ones. So we keep the charges separated, sort of like a tension between them. All the positive charges are separated now from the negative ones. And this is the foundation of creating an electric field, all right? So the idea is illustrated up here at the bottom of page 80 is that charges of the opposite signs collect on respective plates. And we say that the charge accumulated on one plate is stored in the capacitor, right? The total charge on both plates is always zero because they balance each other out of magnitude. So the magnitude of the charges that are positive charges are balanced by an equal number of the negative charges, right? So there's a really nice fluid flow analogy that sort of represents sort of an elastic membrane that separates the inlet and the outlet in terms of how voltage is represented through the capacitance, okay? And that's what we're going to draw next. But this is the foundation of the separating of charges. That's where the energy storage is achieved in a capacitor, all right? So we'll flip over to page 81 now and draw this fluid flow analogy, all right? So in terms of how voltage is accumulated, so the current comes in, how do you represent the accumulation of voltage in a capacitor, right? So the fluid flow analogy is like an inlet here, comes into just sort of a tank, and then we have an outlet, okay? So again, incoming fluid, draining outward through that way. And what happens is the idea of a membrane for which the fluid has to pass through, and it kind of bulges, all right? So you can imagine eventually, you know, it doesn't bulge very much, it's kind of flat, and then as the fluid comes in, it bulges and bulges and bulges. That's exactly this idea of stretching of the membrane is equivalent to the increasing voltage and the capacitance, or in this case, in the capacitor, we'll say that, okay? So that's how the so in other words, the voltage isn't just gonna, it's gonna gradually build up, okay? Similar to how the membrane stretches. For an ideal capacitor, the storage charge is always proportional to the voltage between them, and that produces this new formula, that the charge is related to the voltage by this constant parameter, C, which is the capacitance, okay? Units of capacitance are farads, capital F is the symbol, and they are coulombs per volt, right? So that should make sense because the C constant is going to be charge per volt, and so it's going to be coulombs per volt. The charge Q we represent as the net charge on the plate corresponding to the positive reference. So we just have to have some convention on what the net charge is. So we'll represent that as the positive on the positive reference. So if your voltage is positive, right, then we say there's a positive charge on the plate corresponding to the positive reference. It's a typo there. That should be reference. Okay? Missing a C there, okay? Now, if the voltage is negative, then we say there's a negative charge on the plate corresponding to the positive reference. So again, we designate one of the plates as positive reference, all right? And so if, you know, we just need to specify, you know, which situation do we have, depending upon whether the voltage is positive or negative, okay? So, so we'll mention that in just a second. So we're really hitting at PRC, so we're at. So we're assuming that the current is coming into the positive reference, and if the voltage is positive, everything's fine. If the voltage is negative, then we have to end up getting a negative sign to get energy stored. So a typical range of capacitance would be a picofarad, 10 to the minus 12 farads, to maybe up to femtofarads. Again, very small values, 10 to the minus 15, all right? But be careful, we don't typically get into the femtofarad range, especially in design of computer systems and circuit boards, things like that on computer chips, okay? Right? So let's talk about current. So we're putting all the pieces together. We've sort of illustrated sort of what voltage, how voltage is accumulated, but let's look specifically in terms of formulas and then how we'll draw these elements in a circuit. So current, remember, is the rate of change with time of your charge. So we already knew that. I is equal to dq dt, but since we now have this relationship on a capacitance, that charge is proportional to the voltage, right? Then what we do is we change the Q to CV, take its derivative, and now what we have is this result, that current is the capacitance times the derivative or the rate of change of voltage, okay? So what does that mean is that you're going to generate current as long as you've got a changing voltage. The minute your voltage becomes constant, you have no current flowing through that capacitor. So that's what it says. As the voltage increases, the current flows to the capacitance and it creates a charge on each plate. If you hold the voltage constant, then the current is zero, right? So you're not going to store any more energy, okay? Here's the typical way we'll draw it, and it's kind of makes sense in terms of the design of the capacitor. We represent two plates, and the dielectric layer would be in between them, but you don't need to shade it or anything, just two bars. And we're illustrating the positive plates here, the negative plate is there, and this is PRC, and that we have the current coming into the positive plate, okay? Right? So a capacitor basically reflects an open circuit if you have a DC source. Why? Well, if you have a DC source, your voltage doesn't change, it's constant. And if the voltage doesn't change, then basically you have no current. So that's exactly equivalent to an open circuit, right? So if we have, two terminals and we keep them open like that, yes, there's voltage between them, but there's no current, right? So that's the analogy. Zeroing out a capacitor would be replacing it with an open circuit, okay? So references, if we can move on to page 82, the references for the voltage and the current are PRC, is what we illustrated earlier, okay? Was what I just said, right? I want to indicate something else too, that there's another way you can draw it. And in European designs, they actually like to avoid using plus and minuses for the difference in the plate polarities. So again, typically in an American design, you would see, a current coming in, maybe it changes with time. You have the positive plate, you have the negative plate, right? And you have a certain capacitance, okay? And this is the representation of voltage across it. Again, very much the way we did with resistances. It's the same way, positive, negative polarities, and this represents the plate associated with the positive charge. And European designs, they like to draw it this way, where they, in this gets that membrane into effect, they bow out, or it's like a bow for the negative plate. So this will always be minus, this will be plus, and this will be the current coming in again, I of T. And again, this is PRC as well, okay, for capacitance. It's just the plate that's bent represents the negative. Represents the negative voltage, okay? Again, this is V of T, right? Okay. So what we're gonna do now is just a little simple examples to sort of get a feel for how you accumulate these, given a curve for the voltage, what kinds of charge representations are we gonna get out of it, all right? So let's suppose a certain voltage is applied to a 1 microfarad capacitance. And what we want to do is plot the stored charge and the current through the capacitance in microseconds. So again, notice the scale. When you're dealing with capacitance, you're at a very, very small scale mostly, right? So we'll start off by just drawing what we're representing in terms of a very simple circuit with a voltage source that we apply to a capacitance. So we draw in. This time, maybe I'll represent it with the European design, okay? So this is our capacitance of 1 microfarad, and here is the current flow, right? That would make sense because we're going to deliver energy. It's not going to be PRC to VOT, but it's PRC to store energy into the capacitance, okay? Right? So what else do we know? We know that the charge, in this case, is the capacitance times the voltage, okay? So notice I'm not assuming a DC source now. I'm assuming now that the voltage can change. In other words, if you're given a waveform, we're talking about the fact that voltage is changing. So this is not a DC source. So in that case, there's a change in the charge too, right? So, so what we really have, because it's microfarads, remembering the scale from our table of units, this would be 10 to the minus 6, right? In terms of what a microfarad is. And so that's 10 to the minus 6 times V of T, right? So that tells us something about the scale of the graph for Q of T. So the one thing I'd have to do now is say, well, let's apply a voltage to it. I'm going to do it as a waveform. In other words, again, you'd have to be given, well, what kind of voltage do you want to apply to it? So we're going to apply a specific voltage that changes. So here's my voltage curve. The time unit is indicated as microseconds, okay? And I'm going to go up to 10 volts max, okay? So here again, this is voltage for V of t. So the y-axis here is volts. What I'm going to do is I'm going to make some changes through time. So this is in microseconds, 3, here's 4, and here's 5, okay? So I'm going up to 5 seconds. Here's what I'm going to do. I'm going to sketch this level 10 across here. And what I'm going to do is I'm going to linearly increase the voltage from 0, from the initial, from time 0 up to 2 microseconds in a very linear way. And I'm going to hold it constant for 2 microseconds. You see, coming, just making sure it matches up to the 2 and 4. And then I'm going to drop it to 0 again, okay? All right. So this is clearly non-constant. It's changing depending upon time. So we want to know, well, what kind of charge are you getting into the capacitance when you throw a voltage waveform like this, okay? So through time, this is how the voltage is changing, right? Well, the nice thing is we know from our law here for capacitance is we know that the charge is just a scaled form of the voltage. It's just C times V of t. So the shape of the curves will be exactly the same. And so maybe what we'll do is we'll sketch it right underneath. So there'll be no change in the shape. The difference will be the units in the y-axis, okay? So again, keep the time has to be consistent. So we'll still have to be at microseconds here, okay? So, and in this case, we'll still have a value 10 here. Take out the time units again. Draw at level 10. Again, we are drawing Q of t now. So this will come to 10, this will come to 10. This matches 2 and 4 microseconds. It's exactly the same curve for the charge. It may look a little different just because of my drawings, but it's essentially the same curve. But now you've multiplied by the capacitance, right? So this time the units over here are going to be, in other words, this is 10 to the minus 6, right? Coulombs, right? Not capacitance. I need to be careful here. This is coulombs, okay? So these are micro coulombs. Spelled it wrong. Coulombs. C-O-L, sorry. Okay. Again, because you're going to take this value and multiply by 10 to the 6. Now, if it was just 1, I would have coulombs here. It'd be volts to coulombs, but not with the capacitance. Okay, so in actuality, this curve is at such a smaller scale; it's very tiny, right? So if you were laying this graph on top of this one, it would be so tiny down here, right? But the shape is about the same. So it's very important to notice the difference in scale. Shape is the same, but notice a very different scale difference. I'm micro again, representing 10 to the minus 6, okay? So that's the charge would built up proportionally by that factor, okay? Remember that current flowing through the capacitor. Again, if we wanted to go back to current, in this case, remember, we've already defined it. For this case, we can write a new formula. We know it's the derivative with respect of the charge with time, but in this case, for capacitance, it'll be the constant C times the rate of change or the derivative of the voltage. For this problem, it's 10 to the minus 6 times the derivative of the voltage, okay? All right, and so what's interesting for this waveform is then we can look at, well, then how does the voltage change from the waveform, and what does that tell us about getting current, which we'll draw on page 83, all right? So let's look at it. From time 0 to 2 microseconds, right? It doesn't take hard to see that this, you could simply look at the slope. It's linear, clearly, and you get the slope. And so you could see that what's happening here in terms of the rise or the run is that the derivative or the slope has to be 10 volts divided by 2 times 10 to the minus seconds. Keep in mind, you have to keep these units straight, okay? So the formulas are with respect to seconds and with respect to coulombs and volts and everything. So when you're at a smaller scale, you want to make sure you have that exponent correctly, right? So again, the rise is 10 volts, but the run is 2 times 10 to the minus seconds. The derivative is the same as the slope of that line. And in this case, you're going to have 10 to the minus 6 times 5 times 10 to the minus 10 positive 6, and you would get exactly 5 amps, all right? So, so that tells us that, all right, so from time 0 to 2, you are generating 5 amps, okay, through the capacitance, right? 5 amps are generated. It's constant, but it's generated consistently in that time segment. Then what happens between 2 and 4? Well, when you're at 2 and 4, the voltage got held constant. And therefore we know that, well, if it's held constant, and this is how current works in a capacitance, then that derivative is 0. So you would have absolutely no current. You had 5 amps up to 2 microseconds and then nothing, okay? And then finally, between 4 and 5, what we have is a drop. In other words, you have a negative slope here. So you go, the rise is now negative 10 because you're going down over 1 microsecond change. So it's minus 10 volts over 10 to the minus 6 seconds. So that you take the derivative of that, you get negative 10 sevenths volts per second. So in this case, you take that derivative, which is the slope, same thing from Calc 1, derivative is the slope of the tangent line, right? And so the current in this case is just the C value times that derivative here. And then these two things almost knock each other out. 10 to the minus 6 times a negative 10 to the 7th, and you get negative 10 amps, right? So let's rehash this. What's happening is as the voltage is increasing, we generated current, positive current. When we held the voltage constant, we got no current. And then when we drop the voltage, we got a negative current, okay? And let's think about what that means in terms of the distribution of charges, okay? So we'll move on to page 83, okay? And draw this, and then we'll do one more example after that for this section, okay? So what we're gonna do is we're gonna draw what the current is doing for this capacitance. So let's make an axis here. And you already know it's gonna be positive and negative, so we need to think about how we're gonna represent the y-axis here. So we need to go ahead and make sure we take into account it's gonna be positive and negative, okay? Keep the time the same, the time unit is still microseconds, right? And we are drawing, in this case, amperes, okay? We are looking at a representation of the current function, okay? And so what we did is let's mark the time units again, 2, 3, 4, and there's 5 microseconds, right? And what we determined is you get a constant 5 amps for the first 2 microseconds. So there we are, okay, all right. Now what's interesting is that's from the get-go, all right? That's from, you know, from time 0 to 2 microseconds, you got 5 amps, okay, which is what we just showed. Then you got nothing between 2 and 4, so we could just kind of shade it down here at the bottom a little bit. You've got, it immediately, instantaneously drops to 0. And then what happens? Go back to the previous page, we determined it goes negative, twice the negativity of the 5 amps. And so we'll sketch this down here in terms of making sure we have a fairly accurate graph. So you want to keep your points kind of clear. From 4 microseconds to 5, you've got negative 10 amps. Okay. There we go. So what's interesting from the current, from the current graph, it shows you exactly the behavior, what the capacitance is doing in terms of charge, all right? So again, you're getting this voltage created when the voltage increases. So that was a positive slope on the voltage curve. So when the voltage increases, your charge accumulates. Keep in mind the capacitor is storing energy. So the electric field is building up more charge. So you're accumulating, that's provided you keep changing the voltage in a positive way, right? The minute you show your voltage out, all right, you got no current. So this is a representation of constant voltage. So there is no current flowing. It's holding the charge it had, but no more accumulation, okay? You've held what you got, but you're not going to accumulate anymore because your voltage is 0, right? And then, boom, goes very negative, all right? And so this, again, this curve is due to when the voltage decreases, and the charge is removed or supplied, you could say. So this is a really nice thing about the capacitors is you have now the ability to store energy up, store that charge on the capacitor, hold it for however long you need it, and then at any time, again, you flip the voltage. If you flip the polarity of the voltage, you can start shipping that energy out, those charges, that built up charge to other parts of your circuit, right? So that's very, very valuable, okay, right? And so it's just simply a change of the voltage to trigger that distribution of that energy that was stored, okay? One last example, just from a little calculation standpoint, just says, suppose you had a 2 microfarad capacitor, and there is the charge function, clearly changes sinusoidally. Notice that, again, at the scale we deal with time, it's not unusual to have angles of this magnitude because time's at a very finite, a very minute scale. So 10 to the 5th T, coulombs, sine of 10 to the 5th T, 10 to the 5th T times 10 to the minus 6, right? Find the voltage and the current, and we assume all the angles and radius, okay? So again, using our charge equation, our charge function for capacitance, it's always C times the voltage. Assuming the voltage changes, the charge changes, right? In this case, that constant C, be careful, this is capacitance, not coulombs. So this value is 2 times what? 10 to the minus 6, because it's 2 microfarads, okay? Right? So then V of T, by definition, has to be Q of T divided by that C. So we'll be dividing your charge function by 2 times 10 to the minus 6, because that's what the capacitance is. And let's just write in what the charge function is, 10 to the minus 6 times the sine, 10 to the 5th T, again, divided by 2 times 10 to the minus 6, okay? And very nicely, of course, those two terms go out, and we are left that the voltage is just, we'll say 0.5 or a half times the sine of 10 to the 5th T. That's not unusual. Just like we drew before, they will have the same shape, but they'll be a different scale. So again, the scale here of 10 to the minus 6 weighted by this is a much different scale, 6 orders of magnitude different. We're actually almost 7 orders of magnitude with, you know, a half of sine of 10 to the 5th T. So, but the basic shape is going to be about the same, right? What about current? Well, we know to get current in this case, it's the capacitance times the rate of change of the voltage. You have to take the derivative of the voltage function and multiply your capacitance, okay? So in this case, it's again 2 times 10 to the minus 6 times the derivative of this function. So if we take the derivative of it, we'll still have a half. I'll just write it this way. We still have a half times derivative sine is cosine. So we'll have cosine of 10, keep that angle, and then we have to multiply by that, the derivative of the angle itself with respect to t. And so that's going to be times 10 to the 5th, okay? Just using the chain rules appropriately, right? And then we can clean some terms up here, correct? Because we're going to have the 2 and the 1/2 will go away. You're going to have 10 to the minus 6 times 10 to the 5th times cosine of 10 to the 5th t, right? And now you just 10 to the 6th times 10 to the 5th will just give you 10 to the minus 1, or we'll just say 0.1 times cosine of 10 to the 5th t. And that is your current. What's really interesting here is notice that the charge and the voltage are sine-based functions, but your current will be out of phase with it because it'll be a cosine. Isn't that interesting? The angle is still the same, but they're completely out of phase, right? Interesting. We'll see the more properties of that in the coming sections. But that's the introduction to what a capacitance is and how to current voltage, how are they related across this very wonderful way of accumulating energy across two conducting plates separated by a dielectric layer.